In this talk, I am going to introduce our work on characterizing electrocardiogram signal using capsule networks. Capsule network is a fairly new concept and it promises new directions for deep learning. It also achieves equivariance of the network by introducing dynamic routing between low-level and high-level capsules, and they are proven to be excellent at capturing spatial relations in 2D images. Integrating these abilities for 1D signal, CapsNet could provide a comprehensive and meaningful later representations of 1D signals, which is useful for a multitude of auxiliary tasks. Pathological markers of ECG signals are encoded in the duration, amplitude, shapes, and the intervals of waveforms. So, our main goal is to develop new end-to-end trainable capsule network architecture that can simultaneously classify, encode raw 1D signals, and decode the encoded signal. Our proposed network is based on time-caps layer, which is used to build a molecular architecture of time-cap cell. A time-cap cell contains two time-caps layers and a pattern capsule layer. To learn different types of features, we slice along both the temporal axis and the feature axis to produce two different capsule representations called time-caps A and time-caps B. First, we generate capsules along temporal axis and channel axis to act as temporal feature detectors. This enables the model to separately learn two contrasting types of relationships and fuse them in later stages. Time-caps A contains local temporal information. Therefore, it keeps the sample into one single frame, but it tries to predict the possible feature maps in the next layer. We use a convolutional kernel which can be used to predict the next set of capsules for a given capsule. Capsule B contains local spatial relationships. Therefore, it designs to predict the future and past value of a small segment of the signal. And similar to time-caps A, we use a convolution kernel which can be used to predict the next set of capsules for a given capsule. The decoder network is used as a regularization to the capsule network, also as a generator for the instantiation parameters. We use a split vector as an input to the decoder. This allows us to learn the instantiation parameters as a joint distribution across all the classes. In order to analyze the effect of variation of each instantiation parameter on the reconstructed signal, we added a noise vector to the extracted instantiation vector and reconstruct the perturb vector using the pre-trained decoder network to generate ample variations of the input data sample. We trained the proposed network on MIT BIH arrhythmia dataset, and time-caps was able to achieve on-par classification results with the state-of-the-art. And contrast to the state-of-the-art, our model can classify rare beats with only pre-training samples. These are the reconstruction results for different instantiation parameters. We investigate the quality of the reconstruction with variation of number of instantiation parameters. When number of instantiation parameters increases, it introduces unnecessary artifact to the reconstruction signal. These are the perturb signals generated by our decoder network. Each row represents a different class of ECG rhythms. Center column is unperturbed. Column 5 is perturbed by adding 0.2 to the instantiation parameter 1 vector. Column 6 is perturbed by adding 0.5 to the instantiation parameter 1 vector. Column 7 is perturbed by adding 1 to the instantiation parameter 1 vector. We can observe that irrespective of the class, parameter 1 makes a similar perturbation across all. These are the perturbation on single normal beat. Center column is unperturbed. Column 5 is perturbed by adding 0.2 to each parameter. Column 6 is perturbed by adding 0.5 to each parameter. Column 7 is perturbed by adding 1 to each parameter. The first three rows represent perturbation on parameter 1, parameter 2, parameter 3, and parameter 4, which causes significant morphological changes to the signal. While the last row represents perturbation on parameter 6, which does not produce clinically significant morphological changes on the reconstructed signal. Further, Empirically, we found that insensation parameters with higher variance will cause significant morphological changes, while parameters with low variance do not produce clinically significant morphological changes on the reconstructed signal. Thank you.